Now that we've identified for this short list of expressions here, what are their numerical factors from 2 through 12? Let's see if we can begin to build, for these expressions, the greatest common factor. So looking at expression B here, 18 and 24, we've listed out what their common factors are. What is the greatest common factor between 18 and 24 according to what's up here? 6. So therefore, when we're building the greatest common factor of this pair of expressions, the numerical coefficient of it is going to be 6. It's the largest factor that we find in the column here. And the greatest common factor for the expression D here, 16 plus 40x to the third, what's its coefficient going to be? 8. And the coefficient for the greatest common factor of 24x fourth y to the fourth plus 36x squared y squared? 12. So there we've figured out what the largest number is that we can factor out of the numerical coefficients of these expressions. By the way, what about C? What's the largest number that goes into both 3 and 19? Max?
1.
Yeah, the best that we can do is 1. So there's a pair of numbers that have no interesting common factors at all. We say that they're relatively prime to one another. They don't share any common factors together, except for the one factor that everything shares, 1. So the numerical coefficient for the greatest common factor in C is going to be 1. If we continue down the rest of the list, we'll get 1 for the greatest common factor in x to the fourth plus y to the fourth. We'll get 2 as the greatest common factor in 36x plus 2x squared. We'll get 3 as the greatest common factor between 9y to the fourth and 3xy to the fourth. And we'll get 1 as the greatest numerical common factor between these two expressions here at the very end. So that does it for the numbers. I'll maybe fill in the rest of the check marks while I'm talking here. What else do we need? There's not many x's in the bottom half, is there? What else do we need to figure out when it comes to figuring the greatest common factor of this set of expressions? What haven't we done yet? For these expressions, in addition to the numbers that we can factor out, and by the way, this is the part that takes more thinking, more thought, more work, more lead on your paper, right, is figuring these numerical coefficients out. The next question is, how many powers of these variables can we factor out? If you take a look at the first row here, 6x to the third minus 3x squared. I'm going to dwell on that example for just a second.
Do the signs have anything to do with it?
Good question. Do we care that some of these are pluses and some of these are minuses? And the answer to that is no, not for this particular question, right? If we're trying to figure out what are the greatest common factors of these terms, whether there's a plus sign in between them or whether there's a minus sign in between them, what we're really looking at is this monomial, 6x to the third, and this monomial, 3x squared, kind of just as their own separate entities. Whether they're being added or whether they're being subtracted doesn't matter yet. It will once we actually factor these expressions. But just to identify the greatest common factor, it doesn't matter. We might as well just be listing them out instead of adding them or subtracting them together. So let's take a look at 6x to the third and 3x squared. And I want to kind of give them the factor tree treatment themselves. What we figured out already is what happens if we factor the numerical coefficients of these things. So 6, when we factor it, turns into a 3 and a 2. And the 3, when we factor it, well, doesn't really give us anything interesting because 3 is already prime. And so the greatest common factor that we can make between these two monomials is 3. It's the best that we can do. But what I want to suggest is that we can do the same thing with the variable factors in these expressions as well. What does it mean, after all, to write x to the third power? What are we really doing there? What is x? It's really, multiplying x by itself 3 times. So we could kind of include that as part of our factor tree. Likewise, for x squared is the same thing as x times x. So our question about greatest common factors can really be extended into a question of, in addition to the number 3, what other factors do these two monomials have in common? And that's what's happening next in the table. Do these two monomials have an x in common? They do. So that's why the first box in this row here is checked, right? Both of these monomials are divisible by x, is another way to think about it, right? Because we can see in their factorization, each one of them has at least a single power of x. What about x squared? How can we tell that x squared is a common factor of these two expressions? Yeah, right. So one of the ways to see it is that x to the third really is, in disguise, if you like, x to the third. If we break it apart, if we factor it, it's the same thing as x squared times x, right? X squared times x to the first. Because if we were to multiply those two expressions together, their exponents would add. 2 plus 1 will give us 3. Right? So x to the third is the same as x squared times x, which means x squared goes in to x to the third, and it clearly also goes into x squared. So x squared is also a common factor of these two expressions. So when the full story is told here, the greatest common factor, what we call the GCF, of these two expressions, will include the numerical factor of 3, but it will also include a maximal number of shared x's. And that maximal number of shared x factors is 2 of them. Which is why, in this chart, we can see the greatest common factor of these two expressions is written to be 3x squared. The 3 coming from the greatest common factor of the numbers 6 and 3, and the x squared coming from the greatest common factors of the variable factors x to the third and x squared. Does anybody see a shortcut? A quick way that we could have known that x squared was the greatest common factor of the variable factors of these expressions?
I just knew 3 went into 6, and then x2 was part of x3.
X squared was part of x cubed. Okay, great. So that'll get us a part of the way there, right? Because again, x to the third is the same as x squared times x. So between x to the third and x squared, we picked x squared. Let's maybe look at one more example. What if I were doing the variable factors for part B? 18y squared plus 24y. We decided 6 was the right coefficient to take out. How many powers of y will we be able to take out as the greatest common factor, Max? Yeah, single power, y to the first. So between y to the second and y to the first, we chose y to the first. Between x to the third and x to the 2, we picked x to the 2. What's the shortcut? Which power are we picking every time? The smaller one. So that's the quickest way to remember how many powers go into the GCF. Pick the smaller exponent that you find. Right? Between the exponents of 3 and 2 in the first example, we chose 2. Between the exponents of 2 and 1 in the second example, we chose 1. And the story remains the same as we go through the rest of these parts. All right, so let's take a look at what you got. So for part C, 19x to the fourth y minus 3xy squared. How many x's did you have in your greatest common factor? This side of the room. One. Again, choosing the smaller of the exponents that you saw. And our choices were between x to the fourth and x to the first. So we chose the smaller exponent, x to the first. How many y's did you have in the greatest common factor for C? Same deal. Y to the first power. Because we had a choice between y to the first and y to the second. So our greatest common factor for this expression will be 1xy. For part C, what did you choose for the greatest common factor between 16 and 40x to the third? How many x's did your greatest common factor have? None. Why not? Yeah. Even though there are 3 powers of x in the second term to choose from, there are no x's at all in the first term to choose from. Therefore, our choice is between 3 x's and no x's, from which if we choose the smaller exponent, we choose no x's at all. So the greatest common factor between these two terms is actually not a variable at all. It's just 8. So we end up with no powers of x. Part E, how many x's? Yeah, here we have a choice between 4 powers of x and 2 powers of x. So 2, choosing the smaller exponent. How many y's? Also 2. So there the greatest common factor is 12x squared y squared. How about an f? X to the fourth plus y to the fourth. What is its greatest common factor? Yeah, there's nothing else we can do. We have to choose between 4 powers of x and no powers of x, where we choose none. we have to choose between 4 powers of y and no powers of y, again choosing none. So the only common factor between x to the 4th and y to the 4th is 1. That one's not very interesting, right? Those two terms have nothing at all in common. Part G, between 36x and 2x squared, we end up with x to the 1st. So 2x is the greatest common factor in part G. In part H, we end up with 1 power of x. And how many powers of y do we end up with in part H? 4. So when it says choose the smaller exponent, if both of the exponents are the same, we end up just choosing that same exponent. Oh, you're right. Yeah, I skipped ahead. Thank you for catching me. Why is there no x, by the way? Right, the first term has no x in it. So in fact, no, I don't want an x here. Our greatest common factor is just 3y to the 4th. Thank you for catching me. And then last and certainly not least, how many x's were there in the greatest common factor of these expressions? 2. How many y's? 2. And then the expression on the left had a w, but the one on the right did not, so there's no w's in our final answer. And the expression on the right had a z that the expression on the left does not. And so x squared y squared is the extent of our greatest common factor.